Anton Kolonin, our next speaker. Hello, colleagues. I'd like to speak about data structures and languages for general artificial intelligence. Well, meanwhile, let's begin. When we're working on a business system, we usually use for data storage an SQL database or a relation database, and to describe the interrelations within the system, we use protocols or screen forms. With artificial intelligence, it doesn't work because we don't know in advance what kind of data we're going to store, and we don't know in advance either what kinds of inputs and outputs the system will have. Because if we are working on an artificial general intelligence system, we should be prepared to have this system work with any kinds of data to respond to those inputs with any reaction. If we look at the definition of AGI, I tried to copy what Alexei Potapov did and have a collection of different relevant definitions of AGI. The important thing is for the system or the subject to be able to act in complicated environments, trying to achieve complicated goals. The complexity of the environment will ultimately be defining how general this AI is. More complex environments with more complex goals will require more complex AGI that is able to act in such conditions. We can try to create this basic elementary agent, AGI agent, in accordance with this diagram, where we have a protocol that describes the input data, input information, and the possibility to generate some responses for these input data, and also a database to store some base values of the agent, as well as the sensory information and the responses of the agent with regard to such sensory input, and the observed evidence and the models based on which it responds. It doesn't matter what we use for programming. We could take a neural network model, or we could implement a system based on the functional system theory of Piotr Anochin. This is a reference to my Novosibirsk colleagues, Evgeny Vityaev et al. We could solve such problems and have the system learn very quickly to play Atari breakdown game, to punch back the ball, to eliminate the bricks with a platform. What's important is that with this agent acting in a virtual world, we can describe this world with a number of predicates or a certain set of features that would exhaustively describe the stimuli for the agent that it can receive from the external environment, and also the impact that the agent can generate for the outer environment, thus achieving the goal. If we take multiple agents like this, we could build complex cognitive systems. For example, it could not be about balls and platforms. It could be about strokes and letters. So with strokes as input, the agent should respond with correct letters. So this will be a character recognition agent. Another agent living in the world of letters and words could have as input certain letters, and then it would generate them into words. So there'd be a word generator agent. By building such agents and different relations among them, we could also use different kinds of reinforcement. For example, agents could interact with each other, agreeing on the desirable behavior of the entire system, reinforcing each other, depending on the interagent relations. And if all agents are working in alignment to achieve the goal, they could also receive a global feedback, as is done in the brain cortex, when the correct family of neurons get this endorphin boost as reinforcement. Getting back to this universal AGI model, we see that there are two core elements that we need to create one. First, we will need to be able to store information in one way or another, information about certain universal environments. We don't know which ones in advance. And also we want to be able to receive this information with a protocol or with a language that will describe all possible input states and all possible output states through which the agent will be exerting impact on the environment. If we focus on the structure of data storage, we can see that today the optimal way to represent semantic and neural information is the hypergraph. That is possible to store not just the first-tier graph that only describes relations between nodes and nothing more. This is how the usual neural and semantic networks are built. But for more complex hierarchical systems, we will need hierarchical graphs with a higher level of abstraction described with certain graphs, and then as we dig deeper to lower levels of abstraction, these graphs could be described with more detailed subgraphs, and so on and so forth. Here you can see that any area of knowledge can be presented at different levels of graphic representation, starting with elementary concepts and events that could unite in certain disjunctive and conjunctive sets and sequences. Different sequences of events could also be related with cause and causality. On a second or third level of the hierarchy, or the fourth level of the hierarchy, we could unite them in areas of knowledge, and areas of knowledge could also be united with even higher level relations into interconnected logical subsystems. Then again, if we want to express this knowledge and give the agents the possibility to structurally exchange information about ways to solve problems that each of these agents is tackling, first, we will need a protocol for exchanging this information, and secondly, we will also need a structure for the protocol, a certain framework that would operate the variables, the terms, the motors, and the possible values and definitions that would describe the outer world for this particular agent. For example, we can take a virtual athlete. Its virtual world could be described with certain movements of its legs and arms. On the second level of the hierarchy, the movements of this athlete or a dancer could be united in stunts or in elements of a dance. The dance elements could then be united in groups of elements, and stunts of an athlete could be united into some standard programs. This way, having a possibility to describe with a certain language the system of values, the system of ideas in which the agent is working, we could also transmit information about the environment and the desired changes in the environment, thus ensuring that we have a universal agent that can solve universal problems depending on the behavior and depending on the ontology, the subject matter, and the system of ideas that it has. Another advantage is that if we are building a multi-agent system where each agent has a possibility to communicate with this structured language, if combined, these agents could deal with challenges of the community of society as a whole. For example, we have the system of discovery developed in Novosibirsk by Evgeny Vityayev and his colleagues. This deals with the problems of foraging for mice, virtual mice, obviously. Each mouse learns the correct behavior to eat as much cheese as possible through reinforcement learning, and it fixes this knowledge with a semantic model, semantic value model. Then also each mouse can communicate that correct behavior, that right trick, to the entire community of mice. This way, all mice will be able to use that trick for their benefit. Another application for a semantic or synthetic or structured language for communicating with the agent is where you need efficient communication between humans and artificial agents with artificial intelligence that I have been working on in my project. We proposed this idea back in 2015 at the ML conference, and I was pleased to see last year that that idea was also presented at the AI Journey. Languages of semantic programming or graph manipulation used in semantic web or knowledge graph, these are unacceptable for an ordinary person. These are for specialists, for programmers. Speaking with smart coffee pots or smart cars or kettles with natural language is not yet possible either, because extracting information with the methods that we have is impracticable. And in order to extract structured information, to understand what we need from this smart kettle or what the kettle wants from us, we still cannot reliably say. To communicate with smart things, with Internet of Things, we need simple semantic languages. Humanity has been developing them and developed a few sometime in the past. These are the so-called controlled languages, based on a limited range of vocabulary and semantic constructions that pose no problem for parsing, especially if the grammar of each agent is tied to a specific ontology and the structure of knowledge related to its area of focus. An example of this language is the agent's language, as we call it, developed by us, where any interrogation, declaration, or direction construction in the natural language is, on the one hand, a flat projection of a graph or a subgraph in the area of knowledge that the agent has. On the other hand, it's a simplified representation, emulation of a natural language, Russian or Chinese, depending on the vocabulary that is uploaded in the memory of the agent and tied to the ontology that it uses. As a summary, I can say that today we have a set of ways to create basic ontologies for programming different systemic knowledge areas, and also to store hypergraph and graph information, as well as methods for semantic programming to work with information represented as semantic predicates. And in conclusion, if you're interested in AGI, in AI, we have our Facebook community, and we're also on Instagram. Every Thursday, almost every Thursday, we have an online seminar. If you're interested, please join our project AIJ on AGI agents, founded by yours truly. Thank you. The audience don't seem to have any questions. I will ask my own question then. You said that there are defined and non-defined systems, environments. If we don't have a well-defined problem from the very beginning, how do you enrich your ontological base with terms? There's no such thing as an undetermined environment, because if the agent has, for example, just a video camera, the environment will be defined by the resolution and the the coloring patterns, the channels that the agent is able to perceive that environment with. So if the agent has a camera, that means that defines the environment for it. If, in addition to that, they don't have anything else, the agent doesn't have anything else, such as a channel through which it receives information about what it is doing, if it's good or bad, it cannot learn. For example, with the vehicle that we're working on, at the very least, it should have a video camera and channels through which it can receive input from about the results of its actions, for the agent to understand if it's good or bad, if it's enjoyable, or if it's harmful. And another brief question. We want the agent to be able to speak, but we cannot feed the agent with the entire, with the whole language, natural language, and all its richness. What can we do instead, and at which level? At the very least, the agent should be able to communicate certain actions verbally. Through reinforcement, for example, we should train it that, for instance, to switch on the light, instead of waving its hands, it should say some words. And the more these words resemble the word sound, the more effective is the reinforcement learning. It's the same with Atari. First, we are pretty chaotic with controlling the platform, and then we start learning, by and large, how to play and hit the ball. Thank you. I've just been told that the recording of this video, the recording of the presentation, will be available a bit later. If there were any technical issues, thank you, Anton.